Okay, so I guess we can start, even though officially it is early though, because it's only 3:30, no, 3:50. And we are supposed to start at 4 o'clock. So what should I wait for 10 minutes or continue? Okay. So if anybody sues me, I'm going to tell that you, right. You. Okay. One thing more. If you want to get an excellent solution, then we have to assemble the mass matrix again. So because we have to use mass matrix with R equal to 1 over 12. Oh, but that will give you, implicit method. Let's use explicit method. It will work faster. Let's use explicit method. So let's use beta equal to 0, gamma equal to 1/2. In the new work family of methods, so beta is 0, gamma is 1/2. So this is called, in the literature, this is called central difference method. It's called central difference method because we are evaluating acceleration now. If gamma is 1/2, we are evaluating acceleration at the midpoint. And because beta is 0, so the method is explicit. You do not have to solve a simultaneous set of equations. So we will use lumped mass matrix. And let's take the bar. But size does not matter, whether it is 5 centimeter or 10 centimeter. What matters is how many elements you will take in the bar. So do you want to take 5 centimeter long or 10 centimeter long? It makes no difference in your work. So it's 5 centimeter. Let's say this end is free. No tractions, no loads applied on the right hand. Now on the left hand, some of you were having doubts about how to apply acceleration at the left hand. So let's assume that at this end, u at 0 t is given to be 200 centimeter. No, I need to put time in it. So 2 t square. Meter per second. Actually, if we want to make it really good, we should say kilometers per second, but that will be stretching things a lot. So let's say meters per second. And time t is in seconds. The time t is in seconds. So this thing 2 is really, it has units of 2 over second then. Like it has units of 2 meter over second, something like that. Because meter over second, oh, this is displacement. Sorry, this is displacement. So this is something like this, 2 t square meter. So this number, even though you see this number 2, is really meter over second square. The units of this thing are meter over second square. Otherwise, you don't get consistent quantities. So when you will differentiate with respect to time twice, you will get 4t. Sorry, you will get 4, just 4. So that will mean you are applying acceleration as 4 meter per second square. So this 2 is really meter over second square, even though I did not write that way. So if this number is 2 meter over second square, this number is second, then this has units of meters and is fast enough. We may get in trouble. If we get in trouble, we will lower it. We may, instead of saying 2 t square, we might say 2 over 1000 t square. Remember, with 5 elements, you should not expect a very good solution. So it's just an exercise to see if the wave has even gone from this node to somewhere here. Mathematically, the wave speed should come out to be 5,000 meters per second, because E and rho are the same. But don't count on it, because you really need 1,000 elements, something like that, to get a good solution. And also, I think maybe let's do like this. So it's 2t square minus 4. 0 is less than t. Is less than 2. And then it is 0 afterwards. I don't think we will be able to find the solution for 2 seconds. Chances are not that high. So the reason is the following. If we take, say, 1, 2, 3, 4, 5 elements. So each element, the length of the element is 1 centimeter. Because we have 5 centimeter long bar, so 5 elements, so 1 centimeter. So delta T is going to be 10 to the minus 2 meters over 5 times 10 to the minus 3 meter per second. So it's going to be 1 over 5 times 10 to the minus 8 seconds. So it's 0.2 times 10 to the minus 8 seconds. So if you want to compute the solution up to 2 seconds, you will need something like 10 to the power 9 time steps. But you will see, it will run like this. It probably won't. You blink your eye and you will get the solution. This is nothing. All you are doing is solving. You are doing D1 or A1 equal to something divided by something 5 times. And depending upon the processors you have on your machines, it should not take much time. So you should see maybe at least at time 0, you have applied, this time 0 is acceleration you are applying, because you will be using the explicit method. So you are solving m an plus 1 equal to f. Oh, yeah, okay, you are right. So this is 0.2 times 10 to the minus 5. So it will be, say, 2 times 10 to the minus 6. So you will need million time steps to go up to 2 seconds. And let's see what we get. I'm not sure how this minus 4 will show up, because when you apply acceleration, minus 4 is not going to show up. So even though so we have a discontinuity, kind of. So we are applying acceleration, suddenly we stop it. Because that's what we are doing here then, right? Pardon me? Pardon me? No, see, there was a few questions raised, how will we apply acceleration? So that's why we are imposing displacement boundary conditions rather than the pressure boundary condition. So it's displacement is something like this, you are imposing like that, and then you suddenly are dropping to zero. Let's see what we get. I mean, the main thing is to see initially if you get something moving on to the right at the speed of 5,000 meters per second. Initial displacement is zero, initial velocity is zero. So, yeah, initially displacement is zero and initial velocity is zero. So if you, after the first time step, after two time step, you should see this node moving, possibly this one. These should not move anywhere. And then after 5 times or 10 time steps, you will see maybe 3 or 4 have moved. Of course, I'm mentioning you because that we will not get as good a result as we got for the frequencies. Okay, good luck. क्या डिसिपेशन? हाँ होती है, होगा ऐसे ही तो because in our system we have not included any dissipation, but in real life you have dissipation because you have bolts, you have welding, you don't have a clean bar like the way we are doing it here. But we have not accounted for that in the problem formulation. If we had dissipation, then this term we will have to include here CD dot term. So that's a damping term. Then the problem is how do you find C? And Rayleigh Lord Rayleigh had suggested that you can take C equal to AM plus BK. It's mainly because you can solve the problem easy then. Then what is the value of A and B? That you have to do experiments on the structure to find out what values you should assign to A and B, depending upon in which mode you have damping dominant. For us, our goal is to learn a numerical technique, not necessarily have all the physics in the problem. So that's why I purposely skipped that, because then I will have to write longer equations. But it's in the notes if you have on it. This term is in the notes, but I did not include it in the class.
Not bothered about
No, it's on the right hand side. Come on. It's K dn plus 1 tilde. Without K, how will the motion be communicated from node 1 to node 2, right? Yeah, okay. It's on the right hand side. Okay, good luck. It's all in your hands. I'm done.
But once you No. Yeah, really.
Values are becoming zeros. Time still
ये निकाल निकल गया इनपुट कर देंगे फर्स्ट टाइम कोई मल्टीप्लिकेशन हो गई velocity first time I don't know. निकल गया ठीक है जीवन में तो नहीं है कि डी जीवन अभी तो क्या 100 होता रहेगा जीवन में डी का टर्म नया वाला जीवन में सिर्फ एक्सेलरेशन का टर्म एक्सेलरेशन में सिर्फ डी वन आ गया ना डी टू जो निकलेंगे ये कैसे करना था सर डी टू के लिए वेलोसिटी वाला स्टेप करना पड़ेगा प्रोफाइल स्टार्ट दिया मैंने दो नोट हमारे तीन
So please pay attention. Your mass matrix is something like rho HE. We are using a lumped mass matrix. So you had rho HE over 2, 1, 1, 1, yeah, okay. So this will be 2, 2, 2, and we have 5 nodes, so 1, 2, 3, 4, 5 nodes. Let me see if it is outside is half here or not. Is it okay? Pardon me? Yeah. There's one more 0. So you have A1, A2, A3, A4, A5. That equals F minus K, and K is E over H. 1, minus 1, 0, 0, 0. Minus 1, 2, minus 1, 0, 0. 0, minus 1, 2, minus 1, 0. 0, 0, minus 1, 2, minus 1, minus 1, 1. Dn plus Dn tilde. So this is n plus 1. This is n plus 1. That is at Dn plus 1 tilde. Right? That is your Gordon equation. Is it okay? So when you start, this expression is Dn plus 1 tilde. So at time 0, everything is 0. Except maybe you can say this is 4. Acceleration is 4 at node 1. So if you want to find then D1. So it's D1 tilde, D2, D3, D4, D5. So that's the first time step you are finding, right? That's Dn plus 1. So that's at time delta t. That should equal Dn, which is 0, plus delta t, Vn, which is 0, plus delta t square over 2, and beta is 0, so it should be delta t square over 2, and a n, this is 4, remaining are zeros. Okay? And you know the value of delta t, you took, let's say you took delta t equal to a, because it's like h over wave speed, some very small number you took. So you will get their a square here. अभी तो सुनो तो सही. So that's dn plus 1. So this one should, so this term here is 2a square. Right? Okay. So now let's solve it. We have to have the condition when you solve it that a1 must always come out to be 4. Because that is the condition imposed by you. That's the boundary condition given to you. So if you simplify the right hand side, what you are given is, this is 0 minus e over h 2a square minus 2a square 0 0 0 ठीक है? Is it okay? But the first equation should be a1 equal to 4. So we need to change this term. So you modify the first term, the first entry. So it's 2 over rho h e over h. Basically it should be 2 over h rho h e times 4 with a minus sign, because you have a minus here. Well, let me, so the first entry should be that. Second entry is minus minus plus e over h 2a square 0 0 0. So we have modified this to that. You have to modify the first entries to get a1 equal to 4. We are not doing anything with this second entry and the so on after that. Does it make sense? Now if you solve it, you will get a1 equal to 4. And if you solve it, you will get twice rho h e over 2 a2 equal to e over h 2a square. A is delta t. So you can solve for a2. a3 is 0, a4 is 0, a5 is 0. Is it making sense or not? So you will have numerical values because you have the values of E, you have the values of H is the element size, you have this A, delta T, A is delta T times step size, so you have the values. So what you get is after the first time step, you have this quantity is not 0 and this is not, well, you have found really A's, you have not found D's, you have found A's. So now you go back to this equation again. Now you know the values of A. New values now, right? You know the values at time delta T. So if you want to find D1, D2, D3, D4, D5 at delta T, So you actually this is a twice delta t now. So you will find a twice delta t because you are going to the next time step. You can find from here. You don't need an plus 1 because we have only an plus 1 at delta t. We don't have at the next time step. So you use this. You know D1. Well, actually, D1 we have not. I have to find now D1 from. Because what did we do here? We had A1. We have A. In our language, there 0. Then we have A at 1. Then you find from here now. Now you find D2. So you can find D2 from here. You can find V2 from here. Actually, we are not using V2 anywhere, but in principle you can, because we don't have damping. That's why we are not using it. So what will happen is now your D2 will be updated from here. So if D2 is updated, and when you plug in here, this side will be updated. So now you will get entries which are in the force vector. This entry will not be 0. And this entry will be different from what I have here. This entry will be different from what we have here. We still have to impose the boundary condition that acceleration is 4 there. So you modify this thing basically to the same value. Otherwise, you will not get A1 equal to 4. So we are not using Lagrange multiplier because this equation is trivial. This equation says mass times acceleration equals the force. And if you want acceleration to be 4, you put here mass times 4. Mass of the first node times 4. So what will happen is you will get non-zero entry here, possibly non-zero entry here. So when you find the D's, they will be not zeros at 1, 2, 3, 4, 5 nodes maybe. When you go to the next time step, you will get all D's not 0. Is it making any sense? So you should be able to do by hand for 2, 3 time steps. You don't need a calculator, and then you will see that the disturbance, when you are pulling it, is propagating from left to right after every time step. Unless you find the values, you won't see it. And you have to compute it. And as I said before, you really don't need a computer. You need a computer if you want to compute for like 10,000 time steps or 100 time steps. For 2 or 3 time steps with 5 equations, it's not. All you are learning is that the disturbance is propagating. You are learning the procedure. You are not getting the correct answer. Right? Even actually for 10 nodes, one can do by hand. So you are learning the procedure. And if you want to get a good solution, like wave speed correctly, then as I said in the morning, you need something like 200 or 1,000 elements. You cannot expect to get wave speed with only 4 elements. We were lucky to get the first frequency good, but that the luck does not always help with every situation. So we have to be reasonable. If you want your luck to help you, we still have to do some reasonable effort. And that reasonable effort does not mean 5 nodes. Okay? वो तो किया था, बताता था पहले. We already did it, H over C. But you should not take H over C, you should take half of that value. Because that is the upper limit. The upper limit is H over C. But you should not take that. You should take roughly, and some people recommend 95% of that value. For the 1D problem, it will be okay even if you take 95%. But for 2D problems or 3D problems, we usually take 70%, 80%, sometimes even 10%. I'm sorry, it will be reflected, but you have to do the work. You have to do the work. It will be reflected because remember there is no force here. So when you are pulling it, there will be force experienced by it. But it cannot have any force. So that means it will try to push back. So you will see reflected wave, but again, not with 4 or 5 elements. So you have to really take, now I'm repeating myself many times, something like 1,000 elements, or the more number of elements you will take, the better solution you will get. For that, you need to write a code. So if I were doing it, I will do by hand for 5 nodes. Really do by hand. I will solve the equations by hand. Then I will write the code and compare the solution or the output from my code after every time step. 1 time step, 2 time step, 3, 4, 5. See if my output from the code agrees with my hand calculation. If they don't, then you have to think where is some issue, whether it's in your code or it's in your hand calculation. And once you have resolved that, then you can change in your code. You can say instead of doing from the number of time steps from 1 to 5, you do it from 1 to, say, 100. If everything goes smoothly, which I hope it will, then you can say do it from 1 to 10,000, 50,000, whatever number of time steps you need. I mean, you have a good estimate there, number of time steps. So do it, and then it should do the job. And remember, this has a shock loading because we are suddenly making the acceleration 0. So what's happening is when you are pulling this bar, there's a stopper here. So once you pull it long enough, you cannot pull it anymore, because that's what this one says. The acceleration is 0. Then of course the displacement is 0 after that. Maybe that's not a very good idea, but because then after you have pulled it, you suddenly push it back. That's what the way it is written here. But anyway, the idea was that see if you can see the wave going or not. The idea was not that you are doing a physical problem well, or this is a well-defined physical problem, but the idea was to see if you can see the disturbance propagating from left to right. And unless you do it first with 5 elements, then maybe you can try with your hand calculation with 10 elements. It's not that hard, because it's all, equations are trivial. It's mass times acceleration equal to force. So the only calculation involved is in this term. And this calculation is again simple because all you are doing is multiplying 3 numbers and adding them. So if this were fully populated, then yes, you will have to do more work, but this is only like -1, 2, -1. So the only thing that's changing is this D vector. And okay, good luck. So we don't have a class tomorrow, and then on Monday we will start something new, unless you want to continue with this. But at least Professor Verma doesn't want us to continue with this. So we will, and also to stay with the syllabus, we need to do crack propagation and fracture and meshless methods. So we will cover, because we have 4 days, and probably we will cover. Actually, the topic for Friday, we have already covered. It said functionally graded materials. We have already covered that. Whatever it says there, we have already covered it. So in a way, we did the reverse. Whatever was listed for Thursday, 29th, we covered it on 19th. And we have been covering that all along. Okay, good luck.